Hello there. I'm Karen McFarlane Holman, and this is a sincere pleasure for me to be talking about science fair projects. What kind of project are you going to be making, and then how to carry it out? So, in this short workshop that we're doing here, you will get all the tools you need and know exactly what you need to do to figure out what the project's going to be and then how to carry it out to the end. All right, so we're going to start with our point number one, and that has to do with the topic itself. It's got to be something that is intriguing to your child. And I know sometimes that might be obvious. Of course, you want to do something that's interesting, but it is crucial. And I wanted to share that you want to think long term in terms of however long that you have to carry out the project, whether it's 4 weeks or 8 weeks or longer, that it has to be that fire, that spark that will carry your child through to the end, because there will be times when there's the eye rolls or the sighs of like, really, I'd have to do this today. Okay, so to work, to carry it through, having that spark, it helps so much. And so this is where you really want to think outside of the box. You want to think creatively. What are the kinds of things that they are interested in? And you'd be surprised at how many different kinds of science twists that you can take on topics that might not be obviously so. So they don't have to be into bugs or into flowers or into animals or into beakers where you're doing some kind of chemistry experiment. You can try to think of things that are more creative outside of that. So that is a great place to start, is find out what are their passions, what are the things that they ask about, what are the things that they think about. And if you have it somehow related to that, if you find a project related to that, that will keep them going. Point two with the science fair project. This is where, once you have figured out, generally speaking, some kind of thing, some kind of system, we call it, that you want to study, you actually want something that does have a lot known about it. So this is one of the things of science fair projects, is a lot of times people want to do something totally new, something that's never been done. Well, actually, it's better if you do a science fair project on something that has been studied a lot, because that is going to allow you to put your own twist on it and then compare to all those things that are known about it. Otherwise, if it's something that's never been studied, then it feels more haphazard. You're trying to explain things where maybe you feel like you're almost making it up. You can't really base it on all of the science that's been done before. So it is totally okay to choose something that has, not only okay, good, to study something that has been studied a lot. Okay. Point three. You want to bring in relevance. Okay, let me explain what I mean by that. This is where, when you're choosing the project, it might be fun to go kind of out in left field and do something that you think, all right, no one's done this twist on it. Let's try this. So here's an example. Let's say you are studying paramecium in pond water, and you're counting the live paramecium by looking through a microscope. Okay, so then you perhaps want to see what is the effect of, say, glitter on paramecium. So then you have your pond water and you add glitter, and maybe you add red glitter versus blue glitter, and you see the difference. Okay, so here's where we ask, is this really relevant to something that might actually happen in nature? The chances of glitter going into pond water are pretty small. And then what's the difference between red and blue? It's not going to get anyone really excited about how that could impact or how it's relevant to the world at large. So this is where you think, okay, what about adding something like oil, thinking that there could actually be an oil spill, or there could be a gasoline spill, or something else like that that might actually happen in nature. So always try to think of something that is tied in with something that could actually happen. Point number 4, you want to have methods that are doable. So what I mean by that is, how are you going to study what you're looking at and making sure that it is actually measurable? So for example, let's think about if you were making a battery out of something like a pickle and you had these electrodes in it and you wanted to study the current, measure the current. And depending on what your variables are, say small pickle, large pickle, depending on the experiment you're doing, and you're trying to measure these currents, but let's say the differences of how much the current changes, it might not be detectable with the multimeter that you have that's measuring the amperage, that's measuring the current. And so this is where you either need to find a different way to measure it, or if you get perhaps a different multimeter, if you're able to borrow one from someone that does have a multimeter that perhaps is more precise. And so there are different ways around it. And if you do get stuck in some way, so you have a good idea and you start rolling with it and it just doesn't seem to be measurable, this is where you can pivot. You can change direction. You can reach out to an expert, find a scientist in your community or online and ask them, hey, do you have any ideas? We seem to be making these changes. We're not detecting any change. Do you have any ideas? And so it's always good to have someone that you can reach out to and just bounce ideas around and maybe get some good ways to pivot if something like that happens. Number 5, having a clearly stated hypothesis. So what's really tempting to do is to have a system you're going to study and you're going to do something to it and see what happens, okay? So that's not good enough. You need to be thinking about what you predict is going to happen. So that's one part of it, what you predict. But that's not all of it. You want to also get insight into why that is happening, why you would have that effect. So it's not just randomly throwing things together just to see what goes on. So that is where, when you're choosing your idea, you want to think about what has been seen in the past and what is known about it in the past. And that gives you a little bit of direction as to how you think that it might change and some reasons why. You might end up being wrong with your hypothesis by the end, and that is okay. Also, depending on how long you have for the project, again, 4 weeks, 8 weeks, that there might be time to test a hypothesis, perhaps prove yourself wrong, but then say, all right, let's make a new hypothesis and test that and go from there. There is nothing wrong with that. That is the scientific method. That is what is done over decades and decades of all these different studies that are done on different systems, where that's exactly what the scientists are doing. They're making a hypothesis, they're testing it, they're trying to prove themselves wrong, actually, because if you don't prove yourself wrong, someone else will if you are wrong. And so then being able to go through that process is wonderful. You never worry about it if it turns out that you are wrong, because a wrong answer is information and it does carry you forward. Number 6, only ever change one variable at a time. Otherwise, you won't know what's causing the change. And this isn't just in science. This is also if maybe you're trying to figure out where there's a leak in your home, in your plumbing. And so you might need to do some troubleshooting. It's the same as troubleshooting. So changing one variable at a time lets you hone in on what was that thing you did? What was that change that you made that caused the observable change in the science, in the system that you're observing and studying. Number 7, having a control experiment. All right, so lots of times when you're first starting out and you're doing some science, you're doing some experiments, and you want to get in there. You want to see the weird, unexpected things that might happen. But you want to start with doing that first control experiment, meaning where nothing has changed. This is the experiment that's been done before. And so if you can do that experiment that's well known, that's done before, nothing's changed, nothing's unusual, and you are then reproducing what's known to happen, what's expected to happen, then that actually establishes, it proves that your techniques are correct. You are seeing and corroborating everything that's been done in the past. And so in terms of the lineage of the science that's been going, there's that past that's been done, that previous scientists have done. And then you come along, and there needs to be a bit of overlap there. So they've established a certain observation, you come in, you reestablish it, and then you can trust that your methods are working. And then you go ahead and you make comparisons and you start mixing things up. You start adding in new things that have to do with your project. So that first experiment, that is something that we call the control experiment. It's controlled, it's known, and then everything else you do can then be compared to that control experiment. Number 9, repeat, repeat, repeat. And I say that 3 times because 3 is the minimum amount of times that you will ever want to repeat something. So if you do an experiment, you get a result just once. Maybe you did it correctly, maybe you didn't. You want to repeat it. Okay, so you do it twice, and let's say the results that you see are close. You want to be sure. If you're doing science, you want to be sure. Do it a 3rd time. And if all 3 of those give you the same results, you can feel a lot more confident. Now, if you were in a chemistry lab, you would probably do it 5 or more times. But in the interest of, depending on how much time you have, how much materials you have for your science fair project, 3 is okay. All right, but shoot for between 3 and 5 times of repeating that experiment so that you feel confident in your results. Number 10, this is if you have enough time and you have the gumption, if you're inspired to do this. And that is to take your project one step further. So here's an example. Let's say you are studying mixing turmeric with baking soda, and you're seeing the effect of color change. And then you compare it to higher temperature and you see, oh, what was the effect of raising the temperature? And if you have a hypothesis based on chemical reactions happening faster at higher temperatures, then you could do that comparison. Your control experiment would be that one done at room temperature, at just regular ambient room temperature. And then you would heat it up and you would make that comparison. How fast did the color change occur? So an example of then going one step further would be to do it at the colder temperatures. So that would be another way to bolster your hypothesis. If you're saying it happens faster at higher temperatures, and if it does, then if you go colder and it slows down, there's additional evidence for you. Again, this is if you have the time to add in some extra experiments and take it that one step further. Number 11, this is when you're done. Okay, so this is when you have all of your observations, all of your data, and then you bring them together and you make your conclusions from it. And not only that, you want to share your results. And so this is where you have the opportunity to, if you are presenting in person, or if you're perhaps making a poster that you show to people, or if you're doing something online, whatever the case is, you want to present it in such a way that people follow your whole process. You carry them with you on your journey that you had. So you start with, why did you study this? Why is it interesting? Why is it relevant? You tell them what your hypothesis was. You may have been wrong. And again, that's okay. At the end, you'll give the results. You'll give the grand finale. Were you right or were you wrong? You want to tell them how you did it. What were your methods? And then what was your experimental design, meaning those changes that you made, and what were the results? The very end, your conclusions. You can add in some discussion about that, how you came to your conclusions, what those final conclusions are, and the take-home message. That whole storyline there is going to really carry people along and get them excited about what you did and get them excited about the results that you got. The 12th and final point to your science fair project experience has to do with when things go wrong. And things go wrong in science. I guarantee it. I've been doing this for 30 years, and believe me, it can be frustrating. And so that's why in the beginning, as I mentioned, choosing a project that excites you, that will help carry you through those moments of frustration. It's also really helpful to have a community, people you can talk to. So if there are other families that are doing science fair projects, if you have a mentor, if you have a teacher, if you have a friendly scientist who lives down the street from you, whatever the case may be, that being able to reach out and discuss what's going on. I don't seem to be observing what I thought, or I'm not being able to measure what I thought, or you're just feeling confused, which can happen sometimes. That is okay. So this is where repetition does help a lot, because sometimes you will end up doing the same experiment 6, 7, 8 times in the beginning before you get the hang of it, and then you're able to do it and repeat it more easily. So there is, in the beginning, sometimes a few more hangups, but if you can push on through, forge on through, then the rewards are wonderful, because that's when you really see what did happen and was my hypothesis supported or not. And this is part of where you might feel like, oh, it didn't work. If your hypothesis is not supported, you can have that feeling, it didn't work. And so this is where you remind yourself, did I find something out? Ask yourself in that way, did I find something out? And the answer could be, yeah, well, the answer will always be yes. If you did the experiments and made observations, the answer will always be yes, I found something out. And that thing I found out, my hypothesis was wrong. I didn't see any changes. Not seeing changes isn't bad. It means that you did some experiments and you discovered, you found something out, that those changes you made didn't affect the color or the temperature or whether or not it bubbles or how many paramecium died or how fast, how quickly that thing dropped or whatever type of project you're doing. So I don't want you to feel discouraged if your hypothesis is not supported. That happens all the time in science. And it is actually imperative that we have hypotheses that aren't supported, because that then allows us to say, excellent, duly noted, and let's move on and try that next thing. It's super important. Most of all, have fun with this. That's really what it's all about. You get the process of discovering and seeing what's going on, taking your own ideas, trying them out, getting that hands-on experience and making those observations, and then sharing it in the end. It's so satisfying. I hope you have fun with it. And I am here cheering you on as you embark on your science fair journey. Thank you so much for joining me. I'm Karen McFarlane Holman. I'm a 30-year science educator, 20-year chemistry professor, founder and director of Science Rockstar Kids, and I love science. Everyone is a scientist, and your curiosity makes you unstoppable.